Today we're going to review graphing polynomial functions. So I know you probably don't have a graphing calculator at home, but you do always have access to Desmos.com. Start graphing, type something in, and you can see what your picture will look like. So I've graphed y equals negative x to the fourth plus 7x squared minus 6x over here on the right. I see that the function comes from negative infinity, it goes up and it turns, comes back down and it turns, and then it turns again, heading back toward negative infinity. So it's doing the same as I move to the left and to the right. It's headed toward negative infinity. Also, I have these three turning points. Well, just by looking at the function y equals negative x to the fourth, blah, 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 I can tell a lot about the function's graph. First of all, I know that the end behavior will be the same. Our degree is 4. That's the largest exponent in this function. Because that's an even number, whenever you have an even power, you're going to have the same end behavior. Also, because the largest degree is 4, if you take 1 away from that, you're going to have 3. 3 is the number of turning points. So I know just by looking at the function that I'm either going to have this W shape or an M shape because I have the same end behavior and 3 turns. Because my leading coefficient was negative, I know that as I move to the right, the function will be headed toward negative infinity. So same end behavior means to the right is negative and to the left is negative, meaning that this is going to be the general shape of that polynomial function. Another key feature of the polynomial function is where it crosses through the x-axis. I see that this polynomial function has 1, 2, 3, 4 times that it crosses through the x-axis. Where are those though? So I can look at this function again and do some synthetic division and determine where my x-intercepts are. So my x-intercepts will be maybe somewhere on one of these. I don't know. I'm going to just come up with a bunch of numbers, throw them at you, and then you're going to use synthetic division to figure out which of these truly are the zeros or the x-intercepts of the polynomial function. Well, if I try 4, I put a little 4 out here and then make this like L shape. You're going to drop the first term, and then you're going to multiply 4 times negative 1. That gave me negative 4, and then you add negative 4. Repeat, multiply 4 times negative 4 is negative 16. Add, you get negative 9. Multiply, you get negative 36. Add, you get negative 42. Multiply, you're going to get somewhere in the ballpark of negative 160, which is not going to add with 0 to come up with 0. So only if you have a remainder of 0 have you truly found an x-intercept. So let's try 0. So put your 0 here, line up your numbers. Oh, I wanted to mention that I had to add some placeholders. I didn't have an x to the third term, and I didn't have a constant term. So I needed to add zeros in their places. All right, so synthetic division, the algorithm, you drop, you multiply, and then you add. 0 times 0, multiply, add. Multiply, add. Multiply, add. Sure enough, I came up with a 0. Therefore, I know that x equals 0 is an x-intercept. Yep, I crossed through the x-axis at 0. Okay, let's try another one. How about 2? So line her up, drop the first term, multiply, and then add. Multiply, and then add. Multiply, and then add. Multiply and add. Yep, we came up with another 0. So 2 is an x-intercept. Yep, 2, 4, 6, 8, 10. 2 is an x-intercept. How about negative 3? Drop, multiply, add, multiply, add, multiply, add, multiply, add. I came up with another 0. So far, I have found 3 of my 4 zeros. Now, I'm going to try the last two options. Negative 1 didn't work because I did not end up with a 0 remainder, but positive 1 did. So I ended up with 4 zeros, 0, 2, negative 3, and 1. So if I go back here, negative 3, 0, 1, and 2, yep, I just didn't say them in the same order, but those were my x-intercepts. Something else that I'm going to have you do for me is review extrema. So extrema are high points and low points. So from this function, I know that it's going to have 3 turning points, so I'm going to have 3 extrema. Extrema is just the plural of the word extremes. Because my parabola opens downward, I'm going to have 2 maximum points and 1 minimum point. If you look back in your notes from first semester, we called these either relative or absolute extrema. We're just going to call them extrema, not relative or absolute, because you don't have access to our yellow school calculators that have that, calculate feature where you can determine the actual maximum or minimum point. All right, let's take a look at one more example. Here I have y equals x to the third plus 6x squared plus 3x minus 10. We're going to talk about end behavior. We're going to talk about extrema. And then we're going to take a look at where we're going to cross through the x-axis. And then finally, we'll look at the picture, the actual graph. So remember, the first term is really all you need to know, all you need to look at. My degree is 3, which is an odd number. So that means I'm going to have opposite end behavior. It's going to look either like this or like that. Because my leading coefficient was a positive 1, I know that as I move to the right, my function will be going up. So I'm going to end positive, end up. And then my other end, or as I move to the left, it'll be doing the opposite thing or going down. All right, so can you talk about end behavior? Notice that 3 minus 1 would be 2, meaning that I'm only going to have 2 turning points. This point's going to be a maximum, and this point will be a minimum. I'll have 1 min and 1 max for my extremes. All right, where am I going to cross to the x-axis? Well, let me tell you a little secret. The fundamental theorem of algebra says that if you have an nth degree polynomial, you're going to have n real and complex zeros, or n real and complex places where you're going to cross through the x-axis. So I know that I'm only looking for 3. So I used the remainder, or let's see, what was that called? Rational zeros theorem. I used the rational zeros theorem to come up with some options. We're not going to review that today, but 5, 2, and 1 are all of my possibilities. Those are all factors of 10. I could also maybe have tried negative 10 and positive 10, but let's see if we can come up with 3 of these that will work. So look at my synthetic division here. I tried negative 5, got a 0, so that means negative 5 is indeed an x-intercept. Negative 2, also, it ended up with a 0 as a remainder, so that's for sure going to be an x-intercept. Negative 1, no such luck. Positive 1, yes, that one worked. I found 3 yeses, 1, 2, 3, and I had a third degree polynomial, so I don't even need to try 2 and 5. 2 and 5 aren't going to work because I've already found 3 that will work. So to review, we've decided that this polynomial is going to have 2 terms. It's going to end on a positive note because of the positive leading coefficient. And the other end is going to be doing the opposite, or going down toward negative infinity. We also know that it's going to have a maximum point and 1 minimum point, and x-intercepts at, what did we decide? Negative 5, negative 2, and 1. Well, I plugged the function into Desmos, and here we go. Yep, my end behavior is just as I predicted. I have 1 maximum, I have 1 minimum, and then I have zeros, or places where I cross the x-axis at, well, these are marked off by 2s, 2, 4, 6, 8, 10. So that looks like at positive 1, at negative 2, 4, negative 5. So negative 2, negative 5, and positive 1. That's what I found, negative 2, negative 5, and positive 1. All right, so that's just a review of graphing polynomial functions and using synthetic division to determine where your polynomial function will cross the x-axis. So I'd like you to go to the Google Classroom now, check out the homework assignment, and go to work. Thanks, guys.